Continuing with this series of videos, taking another look at some of the Professor Lewin lectures on physics, electrodynamics anyway, and yeah, just redoing it in some respects. So, related as a coincidence from the last video played at the time it was played, a few hours later, the last video I did, the Electro Boom guy did a video on the Kirchhoff's rule thing about, it all having to equal zero, or essentially just arguing for the conservation laws and kind of rejecting Professor Lewin's implication that there are non-conservative fields in a sense. So I'll leave a link below in the description to that video. Just sort of explains what I poorly argued, that it's about where you're measuring things and how you get your measuring tool to the location that is really deciding what you're measuring. So anyway, it's another measurement problem and another experiment. And this is always a lot of physics seems to be about the fact that there's not enough respect for the difficulty of making measurements sometimes. Anyway, yeah, that's probably enough of a background statement, just very coincidental, and coincidences are interesting, sort of. Anyway, so moving on, lecture 17. Motional EMF. Another notion that there's something to do with motion that's is the phenomenon of magnetism is realized somehow through motion of currents, when there's something that happens before that. That is the creation of the magnetism.
This lecture was arguably the most important of all my lectures. We saw how a changing magnetic field can produce a current, an induced electric field, an induced EMF. And Faraday expressed that in his famous law, his famous equation, which you see there on the blackboard. You select a closed loop in your circuit. Any loop is okay. You attach an open surface to that closed loop. Any open surface is okay. And you then get an EMF in the loop, and that's the time derivative of the magnetic flux through that surface. And the minus sign indicates that the induced current itself produces a magnetic flux that opposes the flux change, and that we refer to as Lenz's law.
Right. So again, it's paramagnetic responses in these conductors, generally speaking, and which means it's not permanent magnetism, means it's not dipoles. And the responding field is a repulsive field, and that's what needs to be understood, unlike with ferromagnetic, where the field created is complementary in the sense that it is attraction rather than repulsion.
Today I will expand on this a lot further. So let's start with a conducting loop and a magnetic field. This is a conducting loop. Let the dimensions be y, x, and let I have a uniform magnetic field. Magnetic field B is like so, and I choose as the perpendicular vector to my surface. This is the surface that I attach to that closed loop. I choose it pointing up.
So again, the surface has really nothing to do with this other than it's proportional to the circumference of the loop. The loop is what's going to be exposed to the field, and that's all. The metal. The metal doesn't detect anything going through or missing or any of that stuff. It's only detecting the stuff that will hit it. And there's a proportional relationship between how much of the conductor will be hit and what the area of the loop is.
And so the angle between the A and B, say is theta, but B is uniform. So the flux, phi B, is defined as the integral of B dot dA over this open surface. Flux is a scalar. It's plus or it's minus or it's zero. Flux has no direction. So the flux, in this case,
it has a charge, basically saying you're either pointing the positive end or the north end of a magnet at something. That's all that meant.
would be xy, which is the area of this loop. Since the magnetic field is uniform, that's a very easy integral. And then I get...
It's never really uniform, so that's another problem with this statement. It's, coming from a direction especially, there's parts of the wire that'll hit by more force and parts that'll hit by less force, technically.
the magnetic field B, and then I get the cosine of the angle. So now, according to Faraday, it is the time derivative of this quantity that determines the EMF. And you can do it in several ways. You can have a dB, the change in the magnetic field. This is the area, A, of the loop. You can change the area. You can have a dA dt. But you can also change theta. You can have a d theta dt. And I will look at those today. This number here, the way I've chosen my dA, is a positive number. If somehow this number increases in positive value, the induced current that is going to run will try to create a magnetic field to oppose the change.
So again, there's no trying to create a field to oppose the change. It's not opposing a change. It's just reacting to the change. So the paramagnetic material feels the force affects the atoms, it basically charges them. The charge is in the repulsive form to the force that's primarily hitting them, north or south, and it creates repulsion as a response, in the sense that the magnetic field it'll now produce is the opposite of the one that hit it. So it's just the charge scenario, essentially, of when this charge is you excrete something, and you're going to end up getting back what you excreted, because you're going to turn the stuff in the other material into essentially a mirror, and then that mirror is going to reflect back at you whatever you're giving it. And so the first move is the force hits the other surface, turns it essentially into a mirror, and now the mirror is going to reflect back the force that you're, whatever dominant force you're irradiating it with.
So in that case, if the flux, which is now positive, is getting larger positive, then the current that's going to run will be in this direction. That's length for you. So it creates...
So again, this association between current and the effect is reasonable in the sense that current or electricity or pushing force through a wire, pressure through a wire, will charge the wire and create a field. But it's being created by a different mechanism than the induction of the charge. So there's two ways you can create the phenomenon. You can force the pressure right into the conductor, or you can induce the charge through a magnetic field.
By itself, this current will create a magnetic field in this direction. And if the magnetic flux, which is now positive, the way I've defined it, were decreasing, then the current would go the other way around.
So again, this idea that there has to be a current isn't a fact. All you're really doing is changing the charge of atoms, that is how much pressure, and they'll just depressurize as soon as they have an opportunity in a conductor. So if the conductor is normalized, then whatever pressure there is will dissipate quickly. That's why the paramagnetic material, the conductors, generally speaking, they don't stay permanently magnetized, because all they really are is being charged.
Last time, I did several demonstrations whereby we changed B. We had the BDTs. And there was one particular demonstration that blew your mind and that you will tell your grandchildren about and that you will always remember.
So again, he's talking about this kind of illusionary experiment where he measured the same 2 points in a circuit and came up with the exact same, two different voltages measuring from the same positions. And that's kind of easily explained as being a sensor or a probe problem. How you get to that surface to measure it. Your measuring tool gets influenced by the field effect you're trying to measure. You're using a field of change in the magnetic flux to induce a current, and that same field is going to affect your probe wires.
I hope. Today, I'm going to change theta, and I'm going to change the area, which will also give me then induced EMFs, and therefore induced currents into a closed conducting loop.
So again, the argument that you need a current, there you can use it in the sense that you can just pretend this is all caused by currents. So you can mislabel the cause, and the mathematics will still work because there's a proportional relationship between that fake cause and the field effect. The field is going to have an effect. It can be converted into an effect that's caused by voltage because the two function the same way in a sense in terms of what they're causing to have happen to the atoms. But that's as far, there is no requirement that there be a current. The current in the wire creates a field for a specific reason, that it changes the atoms. And you can change the atoms without creating a current.
So let me make another
just to emphasize, the change in the atoms is just a change in terms of turning them into monopoles, not dipoles.
drawing of the closed conducting loop. This has length y and width x. And I'm going to rotate this. My idea is that you can see this three-dimensionally. I'm going to rotate this about this axis with angular frequency omega. Omega is 2 pi divided by the period. The period is the time of one rotation. Normally we choose for that capital T. I don't want to do that today because T can confuse you with Tesla. And so I'm going to rotate this around. So the angle theta that you have there, theta then becomes theta 0 plus omega t, going back to 801. And I choose this theta 0 such that at t0, I choose my theta to be 0. And so I have nothing to do with theta 0. So what now is the magnetic flux? This is my loop. I have to commit myself to a surface. Well, I will just choose this flat surface. Just like I did there, I chose that flat surface. I'm free to choose any surface, why not taking the flat one? And so the flux through that flat surface is then the area, which is x times y. That's the area of this loop. And then I have the magnetic field. And then I have cosine omega t.
So, reducing it simply, again, the area just is another way of saying the surface of the conductor, the length or the area, in a sense, of the conductor that's going to be exposed to the field. And then the B is obviously just the field, and then the cosine WT, I guess, will have to do with what angle you're turning it at.
Maxwell tells me it's not the flux that matters. It is the change in the flux that matters. Okay, so d phi dt. I get the A, the area, I get the magnetic field, an omega pops out, and I get a sine of omega t, and I get a minus sign. Normally I don't care about minus signs, because I'm only interested in the magnitude of the induced EMF. I always know in which direction the current will flow. I really do, because I know Lenz's law. So you should never have too many hang-ups on those minus signs. But
All right, whether the current flows or not is part of the question in terms of just recognizing that all you're really doing is polarizing the conductor. So you're, in a sense, pressurizing with the north end and depressurizing with the south end. And depending on how you've exposed something to that, a closed loop wire with no ends, you've pressurized one half and depressurized the other half, or section. And those two sections can't communicate with each other because obviously you're pushing all the water upstream in a sense, and you have a gap where you're doing the pushing. So if you're sweeping water or something, there's a place where there's no water, and then there's less pressure water on one side and high pressure water, higher water on the other. And there's that in-between area where nothing can happen because you're sweeping, you're actively sweeping. As soon as you stop sweeping, well, then the water can naturalize.
since I'm getting a minus sign out of this now here, it would be a little foolish not to put a minus here and make this into a plus, because that then, according to Faraday, is immediately the EMF, and the EMF is changing with time, because you have this sine omega t in here. And so the current that is going to flow, the induced current, which will also be time dependent, is the EMF divided by the resistance in the loop. And this is the total resistance of that entire network. There could be light bulbs in there could be resistances in there, it's the total resistance. And this current, when I rotate this loop, is going to alternate in a sinusoidal fashion. And we call that alternating current, AC. That's what's coming out of the wall. AC.
So another designation that's a little bit problematic, because there's a difference between AC, that is alternating between north and south, and just pulsing north, 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 north. So pulsed DC will work just as well as true alternating AC in terms of allowing the field to collapse so you can repressurize it. So it's like you sweep the water, then you stop sweeping, it naturalizes, then you can sweep water again. But when you're actively sweeping the water, there's a point you reach, an equilibrium point, where your sweeping creates so much of a capacity to create pressure and no more. You can't create any more water pressure with the speed at which you're sweeping. And there's a point we reach it just doesn't do anything. Nothing changes anymore. And the system is sort of dead. And if you don't let it to relax, you can't sweep. So.
Suppose this loop was double. And what I mean by double is the following. That it works like this. Follow my picture closely. I will go slowly. It's like this, like this, like this. So, back. And I close it here. So it's one closed loop, but I have two windings. I have to attach a surface to this
Yes, you just double everything, blah, blah. We've already been there, done that.
closed loop. That's mandatory. Faraday insists I attached an open surface to this closed loop. What will it look like? Well, I advise you to take that, dip it in soap, and look at it. And what you will see then, because the soap will attach everywhere to the closed loop, you're going to see one surface. It's not two separate surfaces. You don't have two separate loops. It's one surface, but sort of...
So it doesn't matter if you made it into two surfaces and you just connected the wires, same difference.
two layers. One is lower and the other one comes on top. And so, the magnetic flux will double now. Because you're going to see that this magnetic field penetrates both this soap film and the one that is below. And so you get twice the EMF. And if you have N windings in one closed loop, capital N, then the EMF that you get would be N times larger. And you can make N 1000. There's no problem with that. I'm going to do a demonstration for you, whereby I'm going to use the Earth's magnetic field and a loop that you see here that has 42 windings. So my capital N is 42. Not just 2 like here, but 42. And it is circular. It has a radius. I think it's about 30 centimeters. Here you have it. It's about 30 centimeters. So the area, pi r squared.
Right. So area becomes kind of important here because you're sort of recognizing that this is a rather large loop. So there's kind of a lot of surface to be collecting. And he's going to just be using the Earth's magnetic field. So he's using a very weak magnet, but a lot of wire, in a sense, proportionally. Like if you made it small, you know, and converted that same area into this small thing, you'd end up with a lot of windings and a lot of, so, you know, I just think you have to sort of think that the reason why this works is because it is a rather large loop.
Which is my capital A. Pi r squared is about 0.28 square meters. You may want to check that. I use the Earth's magnetic field, which is about half a Gauss. So that's about 5 times 10 to the minus 5 Tesla, if we work in SI units. And I'm going to rotate it around with a period of about 1 second. That means omega, 2 pi divided by the period, is then about 6 radians per second. 2 pi, I call that 6 for now. And so what is the EMF that I'm going to get?
So these are just proportional relationships, like in most, you know, this mathematics that's written in a, you know, a formalization of proportional relationships. So just understand that the area really isn't relevant. The circumference, the amount of wire exposed is the part that's really relevant, but there's a proportional relationship, so it doesn't matter which variable you use because they're proportionally related. So I would argue the formalization here isn't getting to the real cause, okay, and it's just using variables that are proportionally related to the real cause.
When I rotate it once around per second, well, the EMF will change as a function of time. We're going to get 42, that's N. We're going to get A, that is 0.28. We're going to get B, that is 5 times 10 to the minus 5. And then we're going to get omega, that is 6. And then we get the sine of 6t. You see the equation there. The only difference is we have a capital N out here because we have N windings in the closed loop. And this number here in front of the sine 6t, you should check that, is about 3.5 millivolts. 3.5 times 10 to the minus 3 times the sine of 60, and that now is in volts.
Right, so a pretty small number. 3.5 times minus 3, so you're talking 1,000th of a volt. Say it's a millivolt, but it's 1,000th, but whatever, close enough. It's a little tiny bit of voltage.
So you get an alternating EMF, positive, negative, and the maximum value that you would get is 3.5 millivolts. If I look at the EMF as a function of time, it would be something like this. And from here to here would then be 1 second, if I really rotate it around in 1 second. And so the current, the induced EMF, according to Ohm's law.
So it's really another proportional relationship to when you're turning it. You know, it's turning into a stronger field, and that's all you're really representing is as it's turning through the magnetic field of the Earth. It's changing from going against the north part to cutting through the south part, and yeah. So the waveness is just a way of looking at how circles turn, but it's not really a representation of anything in the nature of the force itself, except that it gets stronger and weaker, especially as you're reversing it, as you're changing the direction of it through the field.
Is always the induced current times the resistance of the whole loop. So the induced current will also have this shape, of course. And how high that is depends on how large R is. The EMF is independent of capital R. The EMF follows exclusively from those numbers. It's the current that depends on what the resistance is. Suppose now I rotate twice as fast. I double omega. Two things are changing now. For one thing, that the full period now goes from here to here, only in half a second. But there's something else that changes. The EMF now doubles, because look at my equation. It's hiding behind the blackboard, I think. There is an omega in there. It's linearly proportional to omega, because it's the phi dt that matters. The omega pops out. And so you now get double the EMF. So the 3.5 millivolts maximum would become 7. And so if I try to make it...
So speed matters. And that's sort of a... As you're pressurizing something and depressurizing something, obviously the speed at which you do that, you can sort of argue becomes a component of the pressure. The faster you move the cylinder, the piston, the more pressure you're going to create, just because of the movement, not just because the speed with which you move it, not just because of the fact that it's creating pressure.
Drawing of that twice as high here, twice as low here, then you would get something like this. And so this omega is now twice this one. You get double the maximum value of the EMF.
Sort of implying a conservation sense, in the sense that you're going through the same field, you'll collect the same stuff. You're just going to end up collecting it quicker. You'll travel through the same bits of space, and at each one of those locations in space there's a certain field, and you're not going to miss any of them going faster. Faster doesn't mean you miss hitting all those spots. You do collect everything in those spots. So if there was 10 things to collect, you're going to collect all 10 when you go faster. So you're still going to get all that you would get if you went the slower speed. It's like you don't get to collect more or less. So there's always the same amount collected, and you're just collecting it quicker, which makes it look like you're acquiring more, because in a certain amount of time you will acquire more if you can just keep collecting. So it's just becomes a timed equation.
I'm going to show that here. I'm going to improve on my lights. You see there a current meter with its sign sensitive, can go to the right, can go to the left. And I'm going to rotate this loop. When you rotate the loop in a magnetic field, you can even rotate it in such a way that you get no EMF. I can show that to you easily.
So you rotate it east-west, and it's not going to collect anything because it's rotating. The conductor isn't going against the radiation of the field. It's going this way, and the field lines are going this way, and has to cut the lines to collect the lines. Can't collect anything if you're... Can't collect much, let's put it that way. if you're collecting not in the direction that the stuff is lined up in. That's the right way to say that. You have to cross the lines. You can't be with the lines. If you're with the lines, then you don't collect anything.
This is the loop. And if somehow the magnetic field came in like this, if you rotated this loop now around this axis, there would never be an EMF, because the dA and B would always be perpendicular to each other. There was never any flux going through this system. No flux change. But of course...
of course there's a field, but you're cutting through, but it's always opposite too. So whatever you collect on one side, you give back on the other side. And that sort of defeats your purpose.
If you rotate it around this direction, it would be fine. So think about that. Don't fall in that trap. You can rotate in such a way that there is no flux change. We don't have that problem at all.
So that's like approaching the thing with the magnet facing north-south this way. You're not going to get the same effect you're going to get if you face just the north end.
Because the magnetic field here on Earth in Boston doesn't come straight from heaven down, but it comes rather steep. So there's never any problem here. I don't have to worry about that. So here is that loop, 42 windings. The scale there is in microamperes. So if you want to, you can calculate.
So he's talking about the magnetic field coming down. Again, that's just the wrong way to look at it. The magnetic field is being produced by the inside of the Earth. It's coming out as rays of field. And obviously the more as long the illusion is a real, because of the circumference issue, being flat to it doesn't give you as much as being canted to it, in the sense that it is coming out north on one end and south on the other end. And you're pretty far from the two monopoles of the field, and so all he's really saying is, because he's in Boston, he's further down the north end of the magnet, so the effect, the amount of radiation from the red end of the magnet is going to be a lot weaker than the north end. So he's got enough of a difference to collect the difference.
Calculate what the resistance of the loop is when I rotate, but that's really not my objective. I want you to see that when I rotate it, that you get an alternating current. Very modest, because I rotate very slowly. Now I rotate faster, and it's proportional to omega. And so if I rotate faster, you get a much larger maximum induced current. A larger EMF, a larger current. I don't know how fast I can go. This is about as fast as I can go. It's almost up to 4 microamperes max.
The kind of weirdness here is that obviously this ammeter is only collecting an average of the voltage effect, so it's going back and forth much slower than the actual frequency, because it can't keep up with the actual frequency. So it's just basically averaging how much voltage you're getting. So the average voltage is going higher, and that's all it's kind of showing, because it's way behind in terms of its period. So the meter isn't really reflecting the actual how often the cycles per minute or second. It's not showing you the real cycles.
And so we are producing here AC, alternating current. We have slipping contacts here so that the system doesn't break. And we could put a light bulb here somewhere in this line, and then the light bulb may glow.
Have to be a pretty amazing light bulb. I mean, I don't think you get an LED to glow with that little current.
In the United States, what comes out of the wall is 60 hertz. So that means that the current through a light bulb becomes 120 times per second. 120 times per second do you go to the 0 if you have 60 hertz. Does it mean that 120 times per second there is no light from the light bulb? No, it doesn't mean that, because filaments get hot, and so they still glow even when the current is 0.
So again, they, because of equilibrium, get to a point, saturation, and so even when you turn it off, they're sort of a battery of heat. They've stored the energy, and it's going to take them time to release it. And by the time they're starting to, they're releasing it much slower than your capacity to change the voltage again. So they never can play by the frequency you're pumping. The pumping frequency is much too high, so they do what that ammeter does, and they just average out eventually.
But they don't cool that fast. If you take a fluorescent bulb, then indeed the fluorescent tube goes completely off and on 120 times per second. And therefore you can use them very nicely as stroboscope. But of course the frequency is fixed, you can't change the frequency. It's 120 hertz. So now you're getting the idea of an electric generator, or what we call, if you want to, a dynamo, produces AC. You have a turbine.
Or pulsed DC. So again, it's sort of, I think, an important distinction between dipolar, okay, voltage and pulsed polar voltage.
And the turbine rotates conducting loops in magnetic fields. And that, according to Faraday, will then produce your EMF. And that runs our economy. You have a permanent magnet, and you rotate conducting loops, windings, in that magnetic field. The higher your magnetic...
You end up causing charge differentials, monopoles, and you change them from positive pressure, high pressure, to low pressure alternately, just constantly letting the water back, pushing the water back, pushing the water. So obviously your capacity to have something to push is always there because you're just going back and forth. So there's always a pushable, where if you push with DC and you just push in one direction, once you've pushed it, there's nothing left to push. So nothing can change.
Fields, the higher the EMF. The faster you rotate, the higher the EMF. The more windings you have, the higher the EMF. And the larger the area of your loops, the higher the EMF. As you can see on the equation that I keep.
So again, it's not the area that matters, it's the circumference, it's the length of the wire, and they're just using area as a placeholder for the proportional variable, which is the length of the wire.
Hiding. That's where it is. In the United States, we have 60 hertz, as I mentioned, and we are committed to a maximum voltage coming out. That is the maximum value that you get from the alternating voltage of 110 times the square root of 2 volts, and we call that 110 volts. In Europe, we have 50 hertz, and the maximum voltage there in the oscillation is 220 times the square root of 2. You cannot change omega and go faster somewhere where you generate this electricity, because that would have major consequences. Number one, the EMF that comes out of the wall would go up, so you might blow your television, your circuits. But besides that, you would change also the frequency of the alternating current. And there are many systems that run in such a way that they're locked into that frequency. For instance, many electric clocks, and certainly record players, if you still have one, are locked into the 60 hertz. And so if you were to increase omega, your record player would go around faster, and your clocks would go faster.
Most motors that have a permanent magnet in them are dependent on the frequency. The frequency is what's dictating the rotation speed of the motor.
A long time ago, when I came over from Europe, I brought my record player with me. The record player requires 220 volts. So I bought a transformer here to that the 110 volts at my home would become 220. That was fine. And so the record player was happy. It was running, but it ran 20% too fast because I had overlooked that there are 60 hertz here and 50 hertz in Europe. So it was going a little bit too fast, and you know what that means when it goes too fast. It starts to very crazy. You can't even hear the music. And that's exactly what happened with my record player. So, if we look at a power station, as we discussed earlier in this course, and let us suppose to get some numbers, that the maximum EMF that the power station produces, let's say, is 300 kilovolts, which it puts on the line. And let's say we have loops that have an area of about 1 square meter, and that they use magnetic fields which are, let's say, half a Tesla, by no means unreasonable numbers. And if now you want 60 hertz frequency, so your frequency F, 60 hertz, so your omega is about 6 times higher, 2 pi higher, it's about 360 radians per second. If now you have about 1700 windings, and you can check that at home, then you get your 300 kilovolts. Power is induced EMF times current. And with Ohm's law, you can replace E by IR, and so you get I square R.
Power is just the wattage, so you could argue, and it's sort of obvious. I mean, the more field, the more EMF, the more current. It's a way of the EMF is another way of saying the voltage is proportional to the E in that equation. So you're just back to watts equals voltage times current.
This is joules per second. And so someone has to do work. Someone has to put in the energy, for which you need perhaps fossil fuel. You have to burn oil or coal to keep the turbines going, or nuclear energy, or waterfalls, or wind. But something got to keep those windings going, to keep our economy going. A typical power station in this country has about 1,000, produces about 1,000 megawatts, which is about 1,000 times a million joules per second.
Billion.
I have here a generator which is run by manpower. And for this I need a strong man. Who wants to volunteer? You look very strong there. Now you don't want to look at me now. Come on. Every morning we talk a little bit, but now you didn't see me. This is a power generator. Magnetic field, you see the magnet here.
I guess it's strong by taking physics courses standards.
And there are current loops, windings, and when you crank this, you turn those windings into this magnetic field.
It's like he's wearing his father's clothes or something. Why would somebody make clothes with sleeves that are got to be, 72 inches long?
There's a light bulb here, 20 watts. This gentleman is, what is your name? Naveen. That's almost my last name. Can you start turning and see whether you can produce 20 watts? Put your foot on the... Yeah, keep going. Oh man, a little better. Keep going, that's not 20 watts yet. Are you sure you had a good breakfast this morning? He's producing roughly 20 joules per second now. Can you stop a minute? We have 6 light bulbs here. Lewin, be my guest. 120 watts. Man, where is Superman? I see nothing. 120 joules per second. He doesn't even come close. Keep going, man. Keep going. You want me to stop?
Kind of a, whatever demonstration, but yeah, the point is made. That, energy is very interesting in the sense of how much of it there is to get. And how much work we would have to do if we had to put the juice in the batteries. It'd be a lot of work.
Hold it, keep going. Forget it. Forget it. You tried. That's all that matters. But you see how difficult it is to produce 120 joules per second. Now think about it. When you run your 100-watt light bulb at home, and you do that for 10 hours, that is 1 kilowatt hour. That costs you only 10 cents. Would you run that?
It's a bit more expensive now, but still in the cents category. Anyway, so I think good enough place to end, and so we'll pick this up next time and such. The next edition of. So thank you for your attention. Such.